In this video, we are going to talk about movement or motion. Now, motion in histogram filters and in Bayesian filters generally can be divided into two types, an exact motion and a stochastic motion. And as you probably guess, an exact motion is the easiest to explain. Let's say that I know I'm at bin number 3, for example, and now the robot moves 2 bins. So I will move to bin number 5. So if I was certain that my initial position was at bin number 3 and the movement is 100% accurate, I will now be at bin number 5 with 100% accuracy. And it holds true no matter what the initial distribution is. For example, let's say that I sense the color red. So I might be over here and I might be over here. So it is 50% chance to be in this cell and 50% chance to be in this cell. If I move one bin to the right, the entire distribution moves with me to the right. Therefore, it will look something like this. This is very simple when we are talking about an exact motion. But when we are talking about stochastic motions, things start to be more interesting. Now, it is very important to discuss this kind of motion because in our stochastic world, there is no such thing as an exact motion. Motion always adds uncertainty to the system. Let's say it again. Motion always, but always adds uncertainty to the system. So we need basically the motion model of the system. Let's assume that my motion model goes like this. When I move, for example, 2 bins or 3 bins or even 10 bins, there is 90% chance that I'm actually moving those 2 or 5 or 10 bins, but there is also 10% chance that I stay at the initial position. So basically, if I'm sure that my initial position was at bin number 1 and I command the robot to move 2 bins, the posterior distribution will look like this. I have 90% chance that I moved from bin number 1 to bin number 3, 1 plus 2, but now I also have 10% chance that I stayed at bin number 1. Now if you think about it, I started with 100% certainty. I knew that I was at bin number 1, therefore the initial distribution was 1, 0, 0, 0, 0, 0. But now I can be either at bin number 1 or number 3. Again, motion always adds uncertainty to the system. If I repeat the process once more, it will be even stranger. So let's assume that I moved 2 bins and then I moved 1 bin. So the total movement was 3 bins. Again, we start at bin number 1. I should end my journey at bin number 4. But I also could end my journey at the same initial bin number 1. Why? Because it might that the robot failed to move twice. And I can compute the odds. In order to stay at bin number 1, I need to fail twice. There is 10% chance that it didn't move the first time. And there is also an independent another 10% chance that it didn't move the second time. Now, in order to stay at bin number 1, I need to fail the first time and also to fail the second time. So the posterior distribution after 2 movements or 2 fails will be 0.1 square, which is 0.01. This is for bin number 1. And the posterior distribution for the desired bin or bin number 4 would be to move the first time, and the posterior distribution for the desired bin or bin number 4 will be 90% for the first movement times 90% for the second movement, which is 0.81. So we have 0.81 plus 0.01. What about the other 0.18? So it basically is that I can move the first time but fail the second time, or I can move the second time but fail the first time. So again, the concept of stochastic motion is crucial in the world of Bayesian filter. Motion always adds uncertainties to the system. But we need motion because otherwise we won't have a self-driving car. We will have a self-parking car or self-not-moving car. If you look At the last example, again, we started with 100% accuracy. I knew that I was at bin number 1. But now I can be either at bin number 1 or number 3 or number 4 or number 2. Okay? So the distribution is much spreader now than it was in the initial state. The most important thing in the context of stochastic motion is not to come up with the math. The math is relatively simple. The main challenge is to figure out what the right motion model is. Sometimes we will have motion models that have overshoot and undershoot. For example, if I command my robot to move 10 bins to the right, it might move 11 bins, and I might move 8 bins or 9 bins. So if I move more than what I actually wanted to move, this is called overshoot, over the desired location. And if I move less, this is called undershoot, or below the desired location. So again, the most important thing, or the most difficult thing, or the most challenging thing is not to compute the posterior distribution, but to figure out the most accurate motion model. In the problems below, I will ask you to incorporate what we have just learned into a working Python example and figure out from there how the distribution changes when we add movement after movement after movement. Good luck!